Good morning, good afternoon, and good evening, everyone. Thank you for joining us today for the first session of our User Spotlight Series 2.0 event. I'm Katie Sidwell with RTDS Technologies, and I'll be your moderator for this special series of webinars where we put the spotlight on RTDS Simulator users who have applied this technology in interesting projects that span a wide range of power systems applications. If you're not too familiar with the RTDS Simulator, I recommend you visit our YouTube channel. You can search RTDS Technologies in YouTube, and our channel will come up. We have a lot of videos introducing you to the technology generally, and for specific applications as well. You can also find all the videos from our previous User Spotlight series in 2020 in one big playlist. So if you've already binge-watched all the shows on Netflix, you can move on and watch all these great RTDS Simulator user presentations. So today we have two users presenting on protection testing projects, which are both really interesting and quite different. We encourage you to ask questions throughout the presentations. Your questions can be directed to the Q&A widget, and they'll be answered there throughout the program. Then after our two user presentations are done, we'll do a shared Q&A period where we'll flesh out and discuss the responses to your questions. Also, please feel free to introduce yourself in the chat and let us know where you are joining us from today. We have 5 presenters today, which might be a new record. So in the interest of time, I'm going to introduce them with abridged bios, but you can find their full speaker bios on our webpage, on the page for this webinar. So there's a little bit more about their areas of expertise there. We'll be starting our program today with the presentation, Hybrid Testing of Power System Protection Communication over Wireless 5G from VTT Technical Research Center of Finland. Our first speaker is Petra Rouse, who received her MSc in Electrical Engineering from LUT University, Lappeenranta, Finland in 2018, and is currently responsible for the Intelligent Energy Testbed at VTT. She's also a doctoral candidate at the Department of Electrical Engineering and Automation at Aalto University, Espoo, Finland. She's joined by Heli Kokoniemi-Tarkkanen, who received her MSc in Applied Math and Computer Science from the University of Jyväskylä, Finland, in 1995, and has over 28 years of experience in commercial, military, and research projects covering various aspects of wireless communication. She's currently a senior scientist at VTT. Welcome, Petra and Heli.
Thank you, Katie. Good afternoon, everyone. Today we are presenting the hybrid testing of power system protection communication over wireless 5G. My name is Petra Rouse, and I will be presenting with my colleague Heli Kokoniemi-Tarkkanen. We both work as researchers at VTT Technical Research Center of Finland. We present ICT and energy research, more precisely autonomous systems connectivity and smart grid teams. As for the overview, first we will briefly introduce VTT and provide motivation for our research. Then we will introduce our research topic, discuss the methodology and results, and finally provide some information on VTT as a research partner.
VTT is a visionary research, development and innovation partner for companies and the society. Our high-level mission is to use science and technology to ensure good life for people globally and to keep our planet livable and safe. Our aim is to build secure societies and create sustainable growth by solving global challenges. VTT is one of Europe's leading research, development and innovation partners. It is a multidisciplinary research institute owned by Ministry of Economic Affairs and Employment and has more than 2,100 employees. Here we would like to highlight some of VTT's research activities. The uppermost pictures on this slide show some examples of research use cases where VTT's competence in wireless communications and especially 5G have been applied. In these cases, we focus on mission-critical communication on challenging operation environments such as smart city, smart grid, port automation, and next-generation mining. In the pictures below, there are some examples of our research use cases in smart grids, including control and protection, cybersecurity, and artificial intelligence applications. In this presentation, we will focus on smart grid protection. Current connectivity in power systems involves a variety of communication technologies. For critical applications, wired connectivity solutions have mostly been used. However, wireless connectivity solutions would have advantages of lower deployment or maintenance cost and intrinsic redundancy and scalability. 2G, 3G, and 4G cellular networks have been largely used for remote control and monitoring. However, the current communication networks are too limited for the most demanding critical connections. 5G has aroused interest as a potential solution, providing consistent low-latency connectivity and high reliability. The increasing automation and intelligence of the future power systems will be based on accurate and real-time monitoring and measurements. 5G networks are expected to be the enablers in this development, since they contain technology and services targeted to industrial use. 5G has been promised to provide more capacity through enhanced mobile broadband services and to join more communicating devices through massive machine-type communication services. Among the key novelties, ultra-reliable low-latency communication service enables latency-critical operations. In addition, network slicing allows the 5G network to be split into logically isolated networks deployed on single shared physical infrastructure. Energy companies and utilities see this as a clear opportunity to meet a wide range of applications requirements using a common communication infrastructure and to manage different smart grid services. The communication requirements on power system highly depend on the application. For instance, monitoring communication requirements can be easily met with wireless 4G communication. However, the requirements for protection are the most rigorous, high reliability and low latency. In this research, we studied if the state-of-the-art wireless 5G meets the requirements set by the protection communication.
To test wireless 5G capabilities on protection communication, a realistic pilot environment is crucial. The environment must support both experimenting on wireless communication and power system protection equally. Our aim was to support validation and verification of production services by power system and telecommunication component manufacturers, communication providers, and utilities, and to provide the last mile testing before full-scale implementation and rollout. The first experimental setup we implemented in 2017 for simultaneous testing of production operate times and communication network quality of service to truly provide statistical data on the capabilities of wireless technologies for protection communication. This early setup is displayed in the figures. It used a very simple setup for power systems run on LabJack and 4G communication network. This setup needed several upgrades to enable testing of multiple different protection functions, testing of various wireless communication technologies, and unlimited number of recurring tests. To advance the power system part of the setup, controller hardware-in-the-loop simulation on RTDS was implemented. In this hill simulation, protection relays and merging units were used as the devices under test. Thanks to RTDS, we were able to increase the number of inputs and outputs for both analog measurements and digital controls and status signals, and add various protection functions to our test capabilities while having a realistic power system simulated with automated recurring tests. In this setup, we interconnected the hill simulation with 5G communication network.
Our testbed utilizes both the commercial 5G networks and the 5G test network Finland. The 5G test network Finland is a joint initiative and ecosystem for communication network and service research, testing and piloting. VTT is coordinating the ecosystem and hosting one of the test network platforms. Our smart energy testbed has been built to enable simultaneous testing of power system components, communication components, and mobile operator services. By using different wireless routers, networks, and subscriptions, all the services that the mobile networks offer in the area can be reached. Our testbed also has functionality for testing with different types of traffic produced by real devices, traffic generators, and traffic emulation and shaping functions. The testbed is used for investigating effects of different technologies, services, configurations, and even routing solutions to smart grid protection and control. How do we assess the wireless network performance and communication quality of service? For this, we have defined a set of key performance indicators that can be measured using our testbed. The most relevant KPIs for time-critical and reliable communication are one-way latency and jitter, as well as packet loss, connection breaks, and downtimes. The basis for one-way measurements is accurate time synchronization for all the measurement devices. Our research testbed is connected through our test network to the National Meteorology Institute of Finland, which maintains the national time, provides time synchronization services, and develops measurement techniques to ensure consistency and accuracy. Here are simplified illustrations of our smart energy testbed, combining communication networks and power systems. With these setups, we studied 3 different use cases employing 5G for grid protection: line differential protection, intertrip protection, and fault location, more precisely virtual fault passage indication. In the line differential and intertrip protection cases, the IAC 61850 routable sampled value and routable goose were used, and in the fault location case, the IAC 61850 92 sampled value and goose messages were delivered over a VPN connection. Next, we will show short clips on the operation of line differential and fault location use cases.
One of the most demanding communication-based protection principles is line differential protection. Distributed along the medium voltage line, relays exchange measurements of currents with each other. All the relays compare the values independently, alarm in case of differences, and initiate the de-energization of the line section due to faults. Traditionally, locating the faults on the line has required heavy amounts of manual labor, causing power outages to last a long time. With centralized fault location, the problems can be located in seconds. Cost-effective merging units along the power line publish the digitized voltage and current measurements to the centralized smart substation devices, which compute the fault location and initiate the required actions.
Now back to the RTDS configuration. Here you can see screenshots of the RSCAD draft and runtime configurations for the fault location use case. In this use case, it was crucial to generate faults on multiple locations to assess the detection of fault locations. As the main aim was to analyze the protection communication and transmission of fault messages. The power system model could be fairly simplistic. In the industry protection case, we used GTAO card to generate the fault signals, while in the line differential and fault location cases, the GTNet SV card was used to generate the current and voltage measurements, which were amplified with Omicron CMS 356 units. In all these cases, we used GTFPI card to receive the feedback signals. GT-Sync card was used to supply the external time synchronization from the atomic logs to the RTDS. The same time synchronization was also supplied to all the other components in the pilot environment. Lastly, the hill simulation was automated using a RSCAD runtime script, which would deliver fault every other second and record the round-trip times. This enabled running infinite number of recurring tests. Then to the results. These figures displayed were generated with the RSCAD runtime. In the first figure from the left, you can see the fault being generated with the blue line and the impact of the fault with the black line, and the feedback signal to RTDS as the red line. To analyze the latency of the protection communication over wireless 5G, the rising edges of the blue and red lines were deducted from each other to learn the round-trip time of the test. This was furthermore used to assess the protection operate times and compare the results to wireless communication measurement results. The figure in the middle shows the impact of the fault on the phase currents, and similarly, the rightmost figure illustrates the current variation that matches with the fault signal. On the topmost figure, there is a LED panel of the ABB SSC 600 used as an edge device to display directional overcurrent protection operational, which was used in the fault location case.
Then continuing with wireless communication results. Testing of reliability and quality of service for critical communication applications requires long test times that is possible with our new testbed with RTDS. Here are examples of 48-hour measurements in 5G non-standalone network. The two leftmost figures present the probability distribution functions of the one-way latency samples measured for inter-trip protection and averaged over 1 second. These samples were measured for 3 different 5G NSA deployments. The results show differences and variation in the average delay levels. The rightmost figure shows a more detailed example of a latency measurement in 5G non-standalone network for line differential protection. The blue color indicates latencies from relay 1 to relay 2 and red color vice versa. The average delay is around 24 milliseconds for both directions, but the example shows that there are occasional delay peaks that block the line differential operation. According to the hardware in the loop simulation, the faults protected were 99.88% out of 16,000 faults. The time-critical measurements need to be handled in the worst-case manner. Measuring only average delays or round-trip times is not sufficient. For applications requiring ultra-reliable and low-latency communication, one-way measurements and deep packet-level analysis are essential.
To conclude, We would like to collaborate with you in the future. VTT is a neutral and impartial research organization. We can support testing in commercial and test networks. We can support testing of time-critical applications covering machine-type communication, enhanced mobile broadband, and ultra-reliable low-latency communication services. Our expertise covers aspects from physical to application layers, and we have good understanding of vertical needs for time-critical communication. We can offer power system hardware-in-the-loop simulation, including fixed and wireless communication with RTDS. We have a wide selection of ABB relays, grid emulator, and controllable loads available for testing. The lab in which these experiments were conducted is currently available free of charge for your projects via ERICRIT 2 Lab Access. You can find more information on this at ericrit2.eu/VTT. Please contact Petra for further discussions. We have now reached the conclusion of the presentation and would like to thank you for your attention.
Thank you so much, Petra and Heli, for the great presentation, and we'll look forward to hearing more from you in the Q&A. Next up for our second presentation, we have Investigating Inverter-Based Resources Impacts on Transmission Line Protection via Hardware-in-the-Loop Simulation from Quanta Technology. Our first presenter is Jürgen Holbach, who is the Executive Advisor of Protection and Control and the Senior Director of Automation and Testing at Quanta Technology. He has over 25 years' experience in designing and applying protective relaying, and he's an IEEE chairman. He's joined by Zheyuan Cheng, who received his PhD in electrical engineering from North Carolina State University in 2020, and his Bachelor of Science degree in electrical engineering from Nanjing University of Aeronautics and Astronautics in 2015. He's currently a Senior Engineer in Protection and Control at Quanta Technology. And the final speaker from Quanta is Srinidhi Narayanan, who graduated with a master's degree in electrical power systems engineering from North Carolina State University in 2021. Her graduate program capstone project was sponsored by Duke Energy, and she now serves as a protection engineer at Quanta Technology. Welcome, Jürgen, Zheyuan, and Srinidhi.
Thanks, Katie. So the next paper reports on the investigation of inverter-based resources and the impact onto the transmission line protection via hardware-in-the-loop testing with RTDS. My name is Jürgen Holbach, and the co-authors are Zheyuan Cheng and Srinidhi Narayana. The paper is structured in 5 parts. The first part, I will report a little bit about Quanta Technology, give an introduction who we are. Then we will give an introduction of the paper and the contents of the paper. And the third part reports on RTDS modeling and validation of the model and our challenges on this. And then we will report the results of the hardware-in-the-loop testing, and on the final part will be the conclusion of this paper. About Quanta Technology. Quanta Technology is a consulting company here in North America. Our headquarters is in Raleigh, North Carolina, and our mission is to enable your success with industry-best technical and business expertise, with holistic and practical advice, and industry thought leadership. So we are really proud of this, that we were able over the last 15 years to hire some of the industry experts, of the industry thought leader, which defines the industry, have worked in utilities, have worked for manufacturers. So, and right now, Quanta Technology has over 180 employees, and many of them, over 100 of them, have advanced degrees. So, and this, of course, gives us a lot of horsepower to advise utilities in any of their challenges they have today. So, why would you come to Quanta Technology? Quanta is an independent and an objective consultant and we give practical advice to solutions. We are not so much a management consultant, we are really an engineering consulting company, and we advise customers now basically through the whole life cycle of a project or technology or a challenge you may have. And that goes from technology, developing a technology strategy, developing a roadmap to roll the technology out, to a business case, up to the more technical challenges we may have, and planning and doing a conceptual engineering design, doing a system integration, doing a testing with the customers, and goes on up to the life cycle management of your solution. So that means in any aspect, in any project, we can give advice based on the experience we have sampled with the experts in our group. Let me give you some more details on the protection, control, and automation group inside of Quanta Technology, and that is a group the three authors of this presentation are in. And here are our offerings, and I just want to scan through them from the left to the right. So the first offerings we do for customers are helping them in the setting development, their protection setting development. And that can actually go from the plain calculating the setting for them, but also defining maybe their setting philosophy and helping them actually set up a process. So it has actually several flavors how we can support them. The second bullet point here is our support for customers in compliance work. So and there's right now a huge burden for utilities on additional compliance work. And let's say we have done actually some automation in this regards, where we actually can use information which is electronically available for utilities and process them, and so help actually to make this more efficient, this compliance reporting. And in this process, and that is the third bullet point, is the data management and tools we use. And right now we have a lot of electronic data in the utilities. All those ID data are there. All your simulation tools are there. And how to maintain this data and use this data in an intelligent way. That is basically where we can bring a lot of experience to the utilities. And that automatically leads to the fourth bullet point, engineering automation tools. Over the last 15 years, we learned actually that a lot of the tasks done in a utility can be automated. So, and a lot of utilities do some of the stuff still in a manual way, but we help actually now utilities who seek our help and say, you know what, there must be a better way, we need to automate this. Then when it comes to synchronized measurements, I think in Quanta Technology, we had some of the thought leaders who actually helped to develop this technology in the past. And a lot of utilities have actually PMUs installed. And now I think we are right now in the situation that we want to now take this data and do some intelligent application with this. And that is where we also advise customers with. An upcoming trend are digital substations. And I think the trend has started with IEC 650. And right now, a lot of utilities here in North America start to look into IEC 650, and they see now the benefit of this new standard. What is not just a communication standard, but it helps actually now to do things a little bit smarter as what we have done in the past. But again, a lot of utilities are also scared about going this new path because it's quite a drastic change in the industry as well. And we let's say many of our experts have worked in the standard, and we commissioned many of the substations together with our customers. So we have quite experience in this field of IEC 750 and what it actually means now going this route of a digital substation. We develop business cases for customers, help them to understand what they can gain out of this technology. So upcoming also is the advanced analytics. You all know we have a lot of data in the substations, and to be honest, in the past we didn't really use this data for any useful stuff, for maintenance, for fault location, for fault reporting, for let's say asset management. And that is going to change. Utilities more and more get aware they have really good information in the substation, and they want to utilize this data and want to run some intelligent application. And that's, I think, what is right now really a new trend and a new technology what developed out of this. Last bullet point, yeah, we are also involved in innovative solutions. So we are really looking for new applications where we say, okay, we have new challenges. Now we need new applications, and we have, together with customers, developed some new applications, have some patents gained out of this, and continuing to do this with our customers. So yeah, this paper were put together by me, Jürgen Holbach, and by my two co-authors, Sion Cheng and Sridinidhi Narayana. And I will now pass this on to Seun. He will now report basically on the modeling challenges.
Thank you, Jürgen, for the introduction. So the objective of this project is to test the protection setting on a 345 kV parallel transmission line. So this line we have a series compensation, and we have one tap line to a wind farm facility. So in the RSCAD, we have created a reduced system model to include this parallel transmission line and adjacent wind farm facility. So this is a 38 bus system. So we have two data sources that we use to build this system. The first one is Aspen short circuit model, where we use to build the transmission line and the adjacent systems. And we also have a wind farm plant model from the developer, which is in the PSCAD format. So in this model, we also have some IBR vendor model, which is a black box compiled model. We'll talk about this later in the presentation. So the hardware in the loop test in this project involves two relays, the 311L and 411L from Schweizer Engineering Lab. This presentation wants to focus on the unique challenges introduced by the inverter-based resources. The first challenge introduced by IBRs is the limited fault current magnitude. Typically, you can expect the magnitude to be 1.1 to 1.5 per unit. The second challenge is the control-determined current voltage phase angle. Depending on the controller implementation or different control modes, the phase angle relationship could be very different. The third challenge is the different responses in the sequence components. By design, the inverter controller will suppress negative sequence current. The fourth challenge is a nonlinear fault current contribution. Some inverters have hard current limiter that will cut off the peaks in the fault current. The fifth challenge is the standardization. Currently in North America, there's no comprehensive standard to define inverter fault response. These challenges pose a huge impact on the existing line protection schemes, for example, overcurrent, directional, and coordinations. To evaluate the impact of the IBR, we rely on the RTDS to perform hardware-in-the-loop testing. So in the RTDS library, there's a lot of pre-built average and switching IBR models. For example, solar farm and different types of wind farms, and also different type of energy storage technologies. This offers us a great head start on modeling process. We don't need to create IBR models from scratch. And notably, earlier this year, RTDS released their newly developed universal converter models that enable users to simulate switching model in the main step environment. We think this is a huge improvement and has been greatly increased our capability to simulate more IBRs. In this project, we are required to develop IBR models in RSCAD that matches the vendor PSCAD models. The vendor PSCAD model is typically a compiled dynamic link library that is referred as black box model. This black box model is supposed to include actual inverter controller code that can offer credible simulation responses. If you're interested in learning more about vendor black box model, you can read the reference listed in the slide. So matching these black box model is very challenging because inverter parameters, control logics, and protection functions are hidden. We must extensively observe the inverter responses and use educated guesses to speculate this information. In our case, the wind farm has IVR model from different vendors, and their compiled model require different simulation time steps. Therefore, a third-party parallel simulation tool is needed to run the wind farm model. Another important consideration is the level of details needed in the RSCAD. Because modeling every individual turbines in a wind farm will require significant amount of RTDS hardware cores. During this RSCAD and PSCAD model validation process, we have learned quite some lessons. We learned that the rest of the system matters. In our study, we found that the interconnection transformer selection will have a huge impact on the fault current behavior. On the right, we compare the fault current responses between two identical wind farms, but with different interconnection transformers. The fault current is measured at the high side. We can see that the Y delta Y transformer case, the system is able to drive a lot more zero sequence current at the transformer high side during this A to ground fault. This will make a huge difference to the distance relay when detecting phase to ground fault. Depending on the applications, it may be important to accurately represent the rest of the system in your model. Another important lesson we learned is about getting the correct controller response. The PID gains in the controller need to be properly tuned so that the inverter output can be regulated to the desired set point. For example, in the right figures, we compared the out of control response and controlled responses from two identical Type 4 wind farms, but with different PID gains. So in the left column, we see that the ID and IQ reference in the black color, and also the ID and IQ measurement in red color. We see the ID and IQ measurement, they oscillate around the reference signal with the oscillation magnitude of almost 0.5 per unit. The resultant fault current is distorted, and according to the sequence component calculation, the positive sequence fault current exceeded the 1.1 per unit limit and went beyond 1.5 per unit. We also see there is a significant increase in the negative sequence current component. In the right column, in the controlled response, we see the ID and IQ feedback. They are closely regulated at the references, and the resultant fault current is very sinusoidal. The 1.1 per unit positive sequence fault current magnitude is enforced, and the negative sequence current is very minimum. Note that these two controllers, they are all stable controllers during normal operation. For example, changing power outputs, switching on, switching off, changing control modes. Those controllers all respond stably during the normal condition. However, the controller in the left, they're not fast enough to keep up with the fault conditions. Typically, during the fault condition, out of control response is inevitable in the first 1 or 2 cycles because by design, the controller will introduce delays. For example, the phase lock loop will need 1 cycle to capture the phase angle used when generating the modulation wave. Sometimes the measurement feedback, for example, the ID and IQ shown in the figure, those are filtered using time constant. All these factors would delay the inverter to catch up with the fault condition. But after 1 to 2 cycle, the controller should kick in and regulate the inverter outputs. The third lesson we learned is the protection function probing. Protection function in the controller can largely impact the fault response. Therefore, it is important to model these protection functions correctly. In this slide, we listed 3 typical protection functions used in the real-world inverter controllers. The first one is low voltage write-through. Some inverters may be required to comply to certain regulation. For example, in German grid code, tripping permission is defined as a function of voltage magnitude and time, as shown in the figure in the right. The second typical protection function is decoupled sequence control. In this control scheme, inverters can control positive and negative sequence component independently, and they can choose to active inject negative sequence component if needed. Same example in the German grid code, the reactive negative sequence current injection is required during voltage unbalanced conditions. The third typical protection function is the fault current limiter. This example shown on the right is taken from the PSRC Working Group C32 report, as referenced in the bottom. In this example, the fault current magnitude limit is defined as a piecewise linear function. User can expect different fault current magnitude during different error voltage conditions. These are all examples used for this presentation. They are not enforced by any standard in North America in the current stage. So they are all examples, should not be treated as a required modeling considerations for your applications. In our project, we have gone through extensive model matching practice. In the end, we have achieved a close but not exact match against the vendor black box model. In the left figure, we compare the RMS values of the three-phase voltage and current between PSCAD and RTDS simulations. Note that both simulations do not have active fault clearing. The fault is removed after 20 cycles. In the PSCAD model, after 10 cycles, IBR from one vendor tripped based on their proprietary protection functions. In our study, we are more focused on matching the response in the first 5 cycles that is enclosed by the 2 black vertical lines shown in the figure. Based on our hardware-in-the-loop testing, we can expect the relays to clear the fault within 5 cycles. In this A to ground fault, the mean absolute percentage error of the RTDS simulation is 4.6%. On the right side, we calculated and visualized the sequence component responses. We can see that the responses in positive and negative sequence signals are very similar. In this project, due to our RTDS hardware core limit, we must use one wind turbine model with scaling factor to match a wind farm, with wind turbines from different vendors. The final result shown here is of course not optimal. Improvements can be certainly made by developing and validating individual IBR models against each vendor model. However, in this presentation, we want to convey the message that although it is challenging to match a vendor black box model, it is still possible to get a close match. The validated IBR model are then very essential to the hardware in the loop testing, as they will largely dictate the fault current response. In the next part of the presentation, I will pass the ball to my colleague Shri. She will introduce the test plan and also the testing result we find in this project.
Thanks, Shiyun. Now we can take a look at the RTDS setup at our Quanta Technology Lab in Raleigh. The IBR is connected to the grid through a 345 kV transmission line. In our setup, the IBR is connected to terminal A and terminal B is connected to the rest of the grid. We have 2 relays on either terminal protecting this particular transmission line. The relays are SEL 311 and 411L. And our primary protection scheme is the 87L differential scheme. This is connected through fiber optic communication cables. The 21 distance protection element will act as our backup method. This is the RTDS lab setup in the Quanta Technology Raleigh office. We have the relays connected to the RTDS system and hardware in the loop simulation running for this particular project scenario. So we'll be testing the 87L and 21 protection elements for different fault scenarios on our system. We'll consider various fault types and different locations on the transmission line so that there are faults right next to the IBR and also at the far end of the line. We'll also be considering different fault inception angles and resistances. First, we can discuss the impacts of the IBR on the 87L element. These test results summarize different test case scenarios with the fiber optic communication in place and with 0 fault resistance. We can see that all the 4 relays under test operated as intended and protected the transmission line for different scenarios. This table shows faults on the transmission line with the fiber optic communication in place and with the 30 ohm fault resistance. We can see that the 87L element operates successfully for all the scenarios and passes the test. So from this we can conclude that the 87L element passes all our test case scenarios and is capable of successfully protecting our transmission line. But we still need a backup element for this scheme, and for our case it's going to be the 21 element. So to test the 21 element, we have the same setup in our lab but without fiber optic communication in place, and there is no fault resistance on the line. We can see for this case that the relays on terminal A, which is where the IBR is connected, do not operate for any of the fault scenarios. So only the terminal B relays passed this test and terminal A relays did not. We can now further analyze why. So the reasons for the failure are there is no negative sequence current injection from the IBR, and also there is low fault current magnitude coming from the inverter. So this no negative sequence current injection causes a loop selection error in the relay. So here we see a ComTrade file record showing a simulated fault. This is a single line to ground fault on phase A. So we can see that during the fault there is no negative sequence current output from the inverter. We do see some small amount of zero sequence current, but this is because of the star delta star interconnection transformer, and this zero sequence is actually from the grid side and not from the inverter. To improve the reliability of our protection system, we contacted the manufacturer to help us resolve this loop selection error. They were very responsive and helpful, and they had papers published explaining this problem and also proposing appropriate solutions to overcome this loop selection error. This is actually caused by insufficient negative sequence current, and this impacts the negative sequence direction logic in the relay. So we have to make a few setting changes to overcome this, and this should be made on the relays connected to the IBR terminal. So we enable POTT in the relay and added zone 3 settings. Also we enabled the weak infeed and updated our 50 PF and 50 PR settings to improve the relay sensitivity. The manufacturer has provided a specific formula for updating these settings, and they are listed in the reference 2 on this slide. So after implementing the setting changes recommended by the manufacturer, we were able to see an improvement in the performance of the relay. The relay did trip for ground faults, and we can see a record here showing the same. So in conclusion, to improve the reliability of the 21 element, we have to follow manufacturer recommendation, and also we did see an improvement in the performance of this element for ground faults. We should also attribute this success to the presence of the star delta star transformer, which helped inject zero sequence current in our transmission line. However, this solution did not work for face-to-face faults. So further analysis can be performed to come up with a new method of backing up the 87L element, and one such suggestion provided in the PSRC report, the PSRC C32 report, is the use of the undervoltage element. So the lessons learned from this project are that the RTDS simulations using hardware in the loop are necessary for analyzing the effects of IBRs on different protection schemes. We get to know the actual performance of different relays during different scenarios, and this helps us identify weak points and strengthen the performance of our protection scheme. The next point is that matching the black box vendor models of IBRs in RSCAD is quite challenging, and it requires a lot of attention to detail. Also, for our case, The 87L protection element was not affected by the IBR and was able to successfully protect the transmission line. However, the operation of the 21 element is affected by using an IBR source. The relay manufacturer helped improve the reliability for ground faults, but we still need to come up with an appropriate solution to protect the system for face-to-face faults. This can be done by performing detailed simulations and further analysis for different schemes like the 27 undervoltage element using RSCAD and HIL simulations. Thank you.
Thank you so much to our presenters from Quanta for the great presentation. I hope everyone can hear me okay. And I want to thank our audience for your attention today and your great questions. We have some really good questions to get to during our Q&A session. And I just want to remind the audience of a couple housekeeping notes here before we get to that. If you look at the additional materials section in the bottom left, there's a couple of interesting links. The top one will take you to the registration for our next User Spotlight Series, episode 2. That's in January, so you can take a look at that. And there's also a link to a feedback survey. And if you give us some feedback on this webinar, you can be entered into a draw for a prize. So take a look at that as well. Okay, let's get to a few questions. I think we will start with some questions for Petra and Heli from VTT. There was a question about the motivations, the original motivations for looking into 5G for protection applications. Is cybersecurity concerns part of what motivated that? And is it something that you are looking into as well?
Hi, thank you. For this one, we did like consider cybersecurity as well, but it was like the particular project that this presentation was about. Cybersecurity was out of the scope for that one, but we do have other projects where we are considering cybersecurity as well. I would say that, like in terms of the motivation, one thing there was also that with the wireless communication, there is like more options for different type of architectures for the digital substations and the kind of layout for those, and as well as there is less need for cabling. So those were some of the motivations as well for this one.
Excellent, thank you. We also had a question about what challenges you expect in widespread adoption of 5G communication in protection, especially considering that some protection engineers might lack the background in networking.
Okay, yeah, thanks. Okay, so well, one issue here, of course, is that the as it was outlined in the question, so the people from the protection side and the communication side can kind of speak with different language, or it will take some time also to like understand one another and get this deep understanding of like what type of requirements are needed on the power system protection side. But we do believe that this like adoption of 5G would bring in also like the mobile operators and the communication component manufacturers and so on to the work also as a service providers for the substations and so on. So that way it wouldn't be necessary to for the power system engineers to learn everything like related to 5G and so on.
That makes sense. Thank you, Petra, very much. Let's go over to some questions for our presenters from Quanta. First of all, when you were carrying out the matching between the RTDS and vendor models for the IBR controls, are you starting with a standard RTDS wind farm and building off of that, or do you use your own built controls as a starting base? Do we have someone from Quanta, either Jaywan, Trinity, or Jürgen, who wants to talk a little bit more about the modeling?
Hi, Kitty. Yes. Um, so we did start with the RTDS example wind farm model, and we needed to add protection functions to the control loop. But the vendor model does not have the active negative sequence injection, and even if they have one, we cannot use the example model, so we needed to build a decoupled sequence control. But we did use the RTDS as a base.
Excellent. Thank you very much. I think we might have some audio issues on Jayon's end. So if you just want to try, you can hit reconnect or close the browser and reopen it. But in the meantime, I have another question for the Quanta team. Maybe you can talk a little bit about the actual converter modeling. Do you believe that the average model representation of converters is enough for protection system testing, or is it necessary to use the more detailed switching models for thorough testing?
Can you hear me now, Katie?
Yes, we can.
Okay, great. Yeah, so I'm happy to answer this question. So for switching model, I think for our application, because we are required to match the PSCAD switching models, we don't have a choice there. And even if we do, we need to first justify why, what is the accuracy difference between the switching and average model. So we didn't go to that route. So we just directly use the switching model in the RTDS to perform this testing. But to answer your question, I think it depends on the application. For example, the switching model, they will introduce certain harmonics at different frequency. So if your application is about those those factors really matter to your application, you have to use the switching model. But I think for if you're just interested in a sequence component in the fundamental frequency, then you probably can go by with the average model. I think it's really depend on your application. And by using average model, of course, you have advantage of not using a lot of computational load in the RTDS. But I think right now in RTDS, with the universal converter model, you can simulate switching model in the main step environment. That's already reducing a lot of the computational load.
Yeah, thank you. So you mentioned in your presentation that you were using the UCM, and were you using that in the main step environment? Was the switching frequency available in the main step sufficient for your application, or were you using the sub-step environment?
Yeah, I think for our project, we started with a sub-step because I didn't know about that. And but later I find out you can actually use that in the main step. So the switching frequency we're using is 2 kilohertz. I think it's definitely doable in the main step. I'm already using that for another project, but for this project, we're simulating the sub-step.
Okay, that's good to hear. Thank you. Let's go over to a question for Petra and Telly. Could you talk a little bit more about the setup that you had with the Omicron amplifier and the sampled values? I think that's a newer feature of the Omicron CMS products that our audience might not know about. So could you talk about how and why you implemented that?
Yes, sure. So, yeah, basically Omicron amplifiers nowadays, they also come with this option to input directly the sample value streams. So for 2 of the 3 use cases we had, the line differential and the fault location, we chose to use this input method of the sample value streams directly. And then for that one case of intertrip, we used the low-level analog inputs. And I would say, like, as for the user experience, like I found it very nice. Like, in my opinion, it was like the amount of conversions that you needed to do, like to get the amplified output that you needed, was less compared to the low-level analog inputs. And also it was possible then to use the Ethernet cabling directly from the GDNet SV cards to these amplifiers.
Great, thank you, Petra. I think we have time for one more question, so maybe we'll go back to Quanta for this one. I wonder if you could talk a little bit more about the black box aspect. You mentioned there was a third-party software package that was used to simulate the plant model for the inverter controls. Maybe you could talk a little bit about how that worked.
Oh yeah, so for that one, because we have this wind farm that have different type of wind turbines from 2 manufacturers, and we also have actually energy storage from a third manufacturer. So when they submit their vendor model to the developer have to somehow simulate all the the DLLs, the dynamic link library together. And one, I think from the energy storage vendor, they compile their model in such a way that requires a different time step from the other 2 vendor. So if you use PSCAD alone, you cannot simulate all models together. That's our customer. They actually use a software called eTran to parallel the simulation, and I think they use some type of TCP/IP communication between each simulated model to somehow piece everything together. So we actually don't have that third-party software, and we have to rely on our customer to simulate the data, and then we use those as a reference to match.
Okay, that's interesting. Thank you. I think that is all the time we have for today. So I want to thank the audience again and encourage you to sign up for our next User Spotlight Series presentations. They focus a little bit more on renewables and microgrids. And we also have that survey that we'd like you to complete. And actually, the presentation slides from today are also available in that additional materials panel. And as per usual, we will be sending out the recording of this webinar for your own reference, or if you have colleagues that missed it, that want to watch it, that you think might benefit, you can definitely send them the recording. So with that, I want to also thank all of our presenters today. Thank you so much for being with us. And I hope everyone has a great day.